Hello everyone. Welcome to Driven Life Math and Physics. So welcome to part 2 of Uniform Circular Motion. Thank you so much for tuning in, and I hope this will also be beneficial to you. So let's dive right into it. We're continuing from where we stopped. Last time we were talking about the relationship between angular velocity and frequency. We introduced the topic, and then this is where we stopped. That angular velocity, which is omega, is equal to 2 pi times the frequency. And this came from the formula that we discovered, that omega is equal to angular displacement over time. And linear velocity, as we know from linear motion, is displacement over time. Now, let's look at another concept. We want to look at the concept of the relationship between angular velocity and linear velocity. I think you remember when we're looking at arc length, we said that arc length is equal to, so let's look at arc length to begin with. Arc length which is S is equal to theta times r. I think you remember this when we're introducing the concept of angular displacement. We said the length of the arc is equal to the angular displacement times radius, and remember, this is angular displacement and this is the radius of circular path. Okay, so if S is equal to theta over r, let's try to do this. Let's divide both sides by time. Okay, if we divided both sides by time, what will happen is S divided by t will be equal to theta r divided by t. Now I want you to notice something, but S over t is equal to linear velocity, and theta over t is equal to angular velocity. I think you notice this right now. Okay, for those who can see it, let me write it for you properly. S over t, this part is what we're saying is linear velocity, and there's another part here that is theta. Let me write it properly. Theta over t times r. That's what is happening at the right, on the right hand side, and this is angular velocity. So we substitute into that, it will be v equals omega times r. But do you remember that omega, in the previous video we said that omega ended up being 2 pi f. Therefore linear velocity will be equal to 2 pi r times f. So we substitute into that, and this is what we end up getting. Okay, now this is a very important formula because it will help us link linear velocity and angular velocity and frequency, and this can also be linked to you also remember that the angular velocity was 2 pi over periodic time, so this can also be 2 pi r over periodic time. Okay, so all these formulas are very important. Now let's just recap and list the formulas that we've talked about so far. The first one was S is equal to r times theta. This is for arc length or displacement around a circular path, okay, where theta is angular displacement. I think after that we began to look at angular velocity, which was equal to angular displacement over time. Okay, after that we also concluded and reached a point where we said angular velocity is equal to 2 pi over t. Okay, and then we discover that this is also equal to 2 pi f. All right, and then we found a relationship today between linear velocity and angular velocity, which was angular velocity times the radius of the circular path gives you the linear velocity. This can also become 2 pi r f after substituting this formula in there. Also, you can substitute the formula in there, and v can also be 2 pi r over periodic time. So these are the essential formulas on uniform circular motion that we've looked at so far. All right, this is very, very important. Okay, so in the next lesson, what we'll do is, before we go to the next lesson, we'll do an example in here, but in the next lesson, we'll actually look at so many examples on how we can use these formulas. I think I'm excited about that. So let us look at one example in this one and see how far it will take us. Now, calculations. Alright, we shouldn't just be talking, we have to calculate. Okay, so let's look at some calculations. Alright, now the first example we're looking at. I want us to look at this one. Okay, number one. A bicycle will makes 300 revolutions per minute. 300 revolutions per minute, which is, engineering, we love this one, is RPM. Okay, and calculate the angular velocity of the wheel. We're saying calculate the angular velocity of the wheel. Okay, one thing that you need to understand first of all is that, okay, maybe let me just make sure we understand each other. The linear velocity, the units are meters per second. Angular velocity, now let's look at this one first. Angular displacement, the units are radians. Okay, angular velocity is radians per second. Very important for you to remember. And so we are given here the frequency. Okay, what we have is the frequency in RPM, 300 revolutions per minute. The bicycle wheel is turning 300 revolutions per minute. But remember, they want us to find angular velocity, which is in radians per second. So we need to make sure that what we're calculating is in per second. Okay, so the first thing we'll do is that we know that in 1 minute, 1 minute, 1 minute is equal to 60 seconds. Therefore, 300 revolutions per minute will become 300 revolutions over 60 seconds. Okay, so if this goes into that, this cancels with that, and then this into this is 5, so that becomes 5 revolutions per second. Okay, so this is our frequency. This is the frequency given. Okay, so to find angular velocity, remember this, we have frequency, and the formulas for angular velocity are theta over time, but also we have 2 pi over t, and also we have 2 pi f. So in this case, it's clear that the formula we need is that one. Okay, so we'll say angular velocity is equal to 2 pi f. Okay, and this becomes 2 pi multiplied by 5 revolutions per second. Okay, when we multiply this, we find 10 pi rads per second. Okay, 10 pi rads per second, which is equal to 31.4 radians per second. That is your angular velocity. Okay, can you see how we're using the equations? We were given the frequency. The and we made sure that the units were matching. After that, we employed one of the formulas that we've come to derive, and we found the answer as 31.4 radians per second. In the next lesson, we'll do a lot of these problems, and hopefully that will help us understand these concepts more. Thank you so much for watching. Don't forget to like and to subscribe. Thank you.